want you to picture something for me. It's a very specific image, so you kind of have to stay with me here. Picture a tapir.
A tapir, okay.
Yeah, you know that odd animal that looks sort of like a pig, but with a short little trunk?
Right, yeah, I've got it.
Okay, so hold that image in your head. Now imagine that tapir is made entirely of an accordion.
Wait, an accordion?
Yes.
Yeah.
An accordion, like the body is the bellows and the legs are the keys and buttons.
That was bizarre.
Right. Now, if I asked a human artist to draw that, they'd probably, pause, look at me like I'm crazy, kind of map out the geometry in their head, and then sketch it.
Yeah, it would take some real thought.
Exactly. But we are talking about a computer doing it instantly and photorealistically. This isn't just, turning lead into gold. This is sort of the alchemy of the digital age, turning mere words into visuals.
It really is a form of alchemy, isn't it? But, instead of magic, the formula here is just pure math. Specifically, a massive, massive amount of math.
Math and data. So today we are doing a deep dive into the paper Zero-Shot Text-to-Image Generation. This is by Aditya Ramesh and the team at OpenAI.
Yeah.
And this is the work that really kicked off the whole generative AI revolution we're living through right now. I mean, this is the paper that introduced the world to DALL-E.
And what's so fascinating here is just the sheer scale of the ambition. I mean, this paper describes a 12 billion parameter model.
12 billion.
Right. And the mission wasn't just to make funny memes or weird hybrid animals for the internet. It was to fundamentally bridge the gap between language and vision.
To see if a machine could actually understand the world through text well enough to reconstruct it visually.
Exactly. They wanted to know if that translation was even possible at scale.
And crucially, without being explicitly trained to do those specific things, right? I mean, that's the zero-shot part of the title.
Precisely. It's all about generalization. The question was, can the model take concepts it learned completely separately, like a tapir in one set of photos and an accordion in another, and fuse them together in a way it has literally never seen before?
Which is wild. So we have a lot to unpack for you today. We're going to look at how this model actually sees the world using something called a visual codebook.
That's a huge part of it.
Yeah. And then we'll talk about the architecture, which basically treats images like a foreign language. And of course, we have to get into the engineering nightmare it was to actually build this thing.
Oh, the engineering is where the real miracles happen. And naturally, we'll cover the accidental capabilities that emerge.
The happy accidents.
Right. The things the researchers didn't even know the model could do until they, turned it on and just started playing with it.
Like the hedgehog in the Christmas sweater.
Yes.
But we will get to him later. Let's start with the basics. Part 1. The problem with pixels. Because you'd think, why can't we just feed a regular photo into a massive computer brain and say, hey, learn this?
Well, you can, but it is incredibly inefficient. Think about just a standard image, even a really small one, say 256 by 256 pixels.
Which is tiny by today's standards.
Exactly. It's a blurry little square. But when you actually multiply that out, you have over 65,000 individual pixels.
Right.
And every single one of those pixels has 3 color channels, red, green, and blue.
So that's what, roughly 200,000 numbers just to describe that one tiny image?
Roughly 200,000 numbers, yes. Now, if you try to feed raw pixels into a transformer model, and keep in mind, a transformer is the type of architecture used for things like GPT-3, the memory requirements just completely explode.
Because transformers rely on that attention mechanism, right? They want to calculate the relationship between every single data point and every other data point.
Exactly. They look at everything at once.
So the model is sitting there trying to figure out how the pixel in the top left corner relates to the pixel in the very bottom right corner.
Yes. And the computational cost for doing that grows quadratically with the length of the sequence. So if you double the number of pixels, the work doesn't just double, it quadruples.
Oh, wow.
Yeah. It becomes totally unmanageable very, very quickly.
And from what I understand, a lot of that computational effort is essentially wasted, isn't it?
That is the real tragedy of it, yeah. The likelihood objectives, which is the math the model uses to evaluate how well it's learning, they tend to heavily prioritize immediate neighbors.
Okay, meaning what exactly?
Meaning the model spends practically all of its brain power figuring out that, hey, a blue pixel is highly likely to be right next to another blue pixel.
It gets obsessed with the high-frequency details, like the texture.
That's it, exactly. It's staring so closely at the grain of sand that it completely misses the beach.
I love that analogy. It perfectly captures the texture of the sand, that high-frequency noise, but it completely misses the fact that, it's a beach with an ocean and a sunset in the background.
Right. It completely misses the low-frequency structure. And the low-frequency structure is the recognizable shapes and objects that actually matter to us as humans. The dog, the car, the tree.
So how did they actually solve this? Because they couldn't just use fewer pixels or the image would end up looking like some pixelated mosaic from an old 90s video game?
Right. They use a very clever two-stage process. And the first stage involves something called a discrete variational autoencoder.
Or dVAE.
A dVAE, yes.
Okay, let's unpack dVAE without giving everyone a math headache. What does it functionally do?
Think of it as a ridiculously smart compressor. It takes that 256 by 256 image we talked about and squashes it all the way down into a 32 by 32 grid.
Wow, that is a massive reduction in size.
It's huge.
So we go from roughly 65,000 positions down to just about 1,000.
Exactly. But, and this is the absolute key to the whole system, it does not store pixels in that new 32 by 32 grid. It stores image tokens.
Tokens, like words, because usually when we talk about transformers, tokens are chunks of text.
Right. But in this context, they are essentially visual words. Imagine you have a dictionary or code book filled with exactly 8,192 specific visual words.
Okay.
The dVAE looks at a little patch of the original image and says, all right, this patch looks most like visual word number 4,000 in my dictionary. And then it replaces those raw pixels with that single token.
That's fascinating. So it's almost like sketching. Like, instead of drawing every microscopic vein on a leaf, the model just uses a symbol that universally represents leafy texture.
That's a great way to think about it. Or if it sees a sharp, right-angled corner of a table, it just picks the token from the code book that represents 90-degree angle with dark wood grain.
Got it.
And by doing this, they reduce the context size by a factor of 192.
A factor of 192? That is huge for saving memory.
It's a game changer. Now, they do lose some of that high-frequency detail. The absolute sharpest edges might get a little fuzzy because they're approximating everything with these tokens.
But they keep the essence of the image?
Exactly. They keep the shape of the cat, the text on the street sign, the general layout of the living room.
So now the image isn't a grid of colored dots anymore. It's literally a sequence of tokens from this visual codebook. It's essentially a sentence written in a visual language.
That is exactly what it is.
Yeah.
And that brings us perfectly to the second pillar of this deep dive, treating images like language.
Right, because once you've turned the image into a sequence of tokens, you can treat it exactly the same way you'd treat a sentence in English.
Exactly. And this is where the transformer part comes in. The paper mentions they use an autoregressive transformer.
Which is very similar to how GPT-3 works for text.
Yes. They pick the text caption. Let's say the caption is a white cat sitting on a fence, which is converted into up to 256 text tokens.
Okay.
Then they take the 1,024 image tokens that the dVAE just generated, and they just mash them together.
Into one single stream of data. Like, they literally just glue them end to end.
One single stream. Text comes first, and then the image tokens immediately follow. And the model's only job is simply to predict the next token in the sequence.
See, that feels almost too simple to me. It just reads the words a white cat and then it tries to autocomplete the rest of the stream, which just happens to be the image tokens.
I know it sounds too simple, but that is the core mechanism. It models the joint distribution of the text and the image.
Right.
If it sees the text token for cat, it learns over time that the visual tokens following it should look like a cat. It learns the deep statistical correlation between the word cat and the visual patterns of pointy ears, whiskers, and fur.
But to learn that connection effectively, you obviously need a ton of examples. You can't just show it 10 pictures of cats and expect it to fully understand the abstract concept of feline.
Oh no, you need massive, massive scale. For this, they collected 250 million text-image pairs from the internet.
250 million.
Yeah. This included the conceptual captions dataset, which is known for being very high quality, and a heavily filtered subset of YFCC 100M.
Which is that massive collection of FlickR images, right?
Exactly.
So 250 million pairs. And the model itself has 12 billion parameters. That is just a behemoth.
It is a monster. And that sheer size brings us to the engineering nightmare part of the story. You hinted at this in the intro.
Yeah.
You really can't just click run on a model this big and walk away to grab a coffee.
I was reading about the underflow problem in the paper, which honestly sounds like a plumbing issue, but I'm guessing it's math plumbing.
It is entirely math plumbing, yes.
Yeah.
To fit this giant model onto the GPUs, and they were using NVIDIA V100s. By the way, they had to use 16-bit precision.
Okay, explain that for the non-computer scientists listening. 16-bit versus what?
Sure. Computers usually store numbers in 32-bit or even 64-bit formats. That gives you a lot of decimal places, a lot of precision.
Right.
But those highly precise numbers take up a lot of physical memory on the chip. 16-bit numbers are physically smaller. They're less precise, but they take up exactly half the space of 32-bit numbers.
So if you want to cram a 12 billion parameter model into limited GPU memory, you almost have to use 16-bit.
You have no choice.
Okay, so less precision equals less memory used. That makes total sense. What's the catch?
The catch is the underflow. As the model gets deeper and deeper, and remember, we are talking about a very deep transformer network with dozens of layers, the gradients get smaller.
And the gradients are basically the signals telling the model how to adjust and learn, right?
Exactly. They are the learning signals.
Yeah.
But as they propagate backward through the network, they get smaller and smaller.
They shrink.
They shrink dramatically. And eventually, the exponent in that 16-bit format just cannot represent how tiny the number is.
Because it doesn't have enough decimal places.
Right. It's like trying to write a microscopic number on a giant billboard using a massive paintbrush. You just run out of space to be that precise. The computer just throws its hands up and rounds it down to 0.
It just says, well, this number is so small it basically doesn't exist anymore.
Exactly. That is underflow. And if your gradients hit 0, your model stops learning entirely. It just dies. The training creates a flat line.
That sounds terrifying, especially if you've just invested millions of dollars in compute time. So how did they fix it?
They had to develop a very specific technique called per-Rees block gradient scaling.
Okay.
Instead of treating the whole network exactly the same, they essentially scaled the gradients differently for different parts of the network, specifically in the residual blocks.
To keep the numbers within a range the 16-bit format could actually read.
Yes.
It's almost like using a magnifying glass on the tiny numbers before they disappear into the void.
That's a really good way to visualize it. It amplifies them just enough to keep the learning signal alive. But that wasn't even the only hurdle.
Oh, there's more.
They were training this massive thing across 1,024 GPUs simultaneously.
1,024 GPUs. I can't even imagine the electricity bill for that. But the communication between those GPUs has to be a major bottleneck, right? Because if they spend all their time just talking to each other, they aren't crunching numbers.
You hit the nail on the head. They have to constantly share what they've learned with each other to synchronize the gradients.
Right.
To make that actually efficient, they use something called Power SGD. It dramatically compresses the gradients before sending them over the network to the other machines.
Like zipping a huge folder before you email it to a coworker.
Exactly like that. It reduced the bandwidth needed to communicate significantly. Without these specific engineering tricks, fixing the underflow, compressing the communication, the whole theory would have just remained a theory. They physically wouldn't have been able to train the model.
It's pretty amazing that the magic of AI so often just comes down to really, really clever engineering to stop the math from breaking.
Always. The theoretical paper is one thing, but making it run on actual silicon is another beast entirely.
Okay, so they built the beast. They successfully trained it on 250 million images without it flatlining. Now comes the fun part. What could this thing actually do?
The real headline here is the zero-shot performance. To prove this architecture worked, they tested the model on the MS-COCO dataset.
Which is a pretty standard benchmark test for image generation.
Very standard. But crucially, they did not train DALL-E on those specific MS-COCO captions.
Wait, they didn't train it on the test?
No, and it still worked incredibly well. In fact, human evaluators actually preferred the images from this zero-shot model over previous models like DFGAN or ATTNGAN that actually were explicitly trained on those exact captions.
So it beat the specialized models at their own game without even practicing the game beforehand.
Yes, it was a landslide. 90% of the time, the human judges said this model's images were more realistic. And 93% of the time, they said the images matched the caption better than the specialized models.
That is an absolute blowout. And I think that brings us perfectly back to our accordion tapir from the intro, because this touches on what the paper calls combinatorial generalization.
This is definitely one of the most exciting capabilities they found. The model clearly understands the isolated concept of paper, like its shape, its texture, its snout. And it also understands the concept of an accordion.
Right.
But the paper shows that when you prompt it with a tapir made of accordion, it doesn't just awkwardly paste a picture of an accordion next to a picture of a tapir.
Yeah, I'm actually looking at the figure from the paper right now. It literally draws a tapir where the main body is the folded bellows of the accordion, and the legs are the keys. It profoundly understands the geometry of both things and seamlessly fuses them together.
Exactly. It's actively applying the texture and the mechanical structure of one object to the organic form of another.
Which requires a level of abstraction that I don't think people necessarily expected from just predicting the next token.
No, we really didn't. It's not just memorizing data, it's synthesizing entirely new concepts. It has a functional understanding of how these objects would occupy physical space.
And another great example they give is a neon sign that reads backprop. Now, usually, AI famously struggles with rendering text. We've all seen those generated images where the street signs are just alien gibberish.
Right, it usually looks like a weird foreign language. And to be fair, this model isn't completely perfect at it either.
But it gets close.
In many of the samples, it successfully rendered the glowing neon tubes in the exact shape of the letters BACKPROP.
That's incredible.
It understands that the letters are physical objects that can be bent and lit up. It captured the actual materiality of the neon glass.
Okay, but here's my absolute favorite example from the entire paper. This is the variable binding test. So the prompt was an illustration of a baby hedgehog in a Christmas sweater walking a dog.
Ah, yes. This is a classic linguistic trap for AI.
Because you have two nouns in the sentence, right? The hedgehog and the dog. And you have one attribute, the Christmas sweater. Syntactically, the way English works, the sweater is attached to the hedgehog.
Right. But if you were just a dumb statistical model looking for keywords, you might see the words dog and sweater in the same prompt and just put the sweater on the dog.
Because there are probably a million more pictures of dogs and sweaters on the internet than there are hedgehogs and sweaters.
Exactly. The statistical bias is huge.
But the model got it right.
Most of the time, yes, it actually did. It consistently put the sweater on the hedgehog and left the dog plain.
Which is mind-blowing.
It really shows that it understands the underlying grammatical relationships. It successfully binds the variable, the sweater, to the correct noun in the syntax tree.
Now, I will say the paper does admit it's not totally foolproof. Sometimes it got confused and put sweaters on both of them, or it just grew a big hedgehog walking a smaller hedgehog.
Which is objectively adorable, even if it's technically a failure of the prompt.
True. Very cute.
But the fact that the variable binding capability is there at all, without any explicit training on grammar or syntax trees, is highly significant. It implies the model is genuinely parsing the structure of the sentence, not just word spotting.
And then there are the skills that they just emerged spontaneously, things the researchers didn't even know to look for when they started.
Yeah. The image-to-image translation is probably the most striking one here. Remember, this whole architecture is fundamentally a text-to-image model. It's designed to take words and output pictures.
Right.
But the researchers discovered they could actually feed it a partial image along with the text prompt, and it would flawlessly complete the task.
Okay, walk us through the cat sketch experiment, because this blew my mind when I read it.
So they took a standard photograph of a cat. They fed the model only the top half of that photo, just the raw pixels, which were converted to tokens by the dVAE.
Okay.
Then they gave it a text prompt that said, the exact same cat on the top as a sketch on the bottom.
And the model just drew the rest of the cat, but rendered as a pencil sketch.
Yes. It kept the exact pose, the specific shape of the ears, the angle of the head, everything was spatially consistent. But it completely switched the artistic style to a pencil sketch for the bottom half.
That is wild. That implies it recognizes the core object, the cat, independent of the medium it's rendered in. It has an internal abstract representation of catness that it can render in photorealism or as a pencil sketch, basically, at will.
It actually goes even deeper than that. They found they could change colors, convert daytime photos to grayscale, or even flip entire images upside down, purely using text prompts.
Wow.
And think about it. For the model to seamlessly change only the color of the cat without tinting the background grass, it effectively has to perform object segmentation.
Segmentation. Okay, that's computer vision speak for the model, knowing exactly where the object ends and the background begins, right?
Exactly. Usually, if you want an AI to do that, you have to train a model specifically for segmentation using incredibly complex masks and labeled data.
Literally humans sitting there drawing tight circles around cats for thousands of hours to teach it.
Exactly. But this model learned it implicitly. It learned to cleanly separate the cat pixels from the grass pixels just by reading millions of captions and looking at the corresponding images.
See, that is the real aha moment for me in this deep dive. They didn't explicitly teach it to segment images. It spontaneously learned to segment images because that happened to be the most mathematically efficient way to predict the next token.
Precisely. It is a pure emergent property of scale. It figured out on its own that understanding the physical boundaries of an object helps it solve the autocomplete puzzle better.
It's incredible. However, we do have to be fair here. It's not magic, and it's not all perfect.
Yeah.
The paper is very upfront about the limitations, and we shouldn't walk away thinking every single output from this model is a flawless masterpiece.
No, definitely not. We shouldn't think that you type a prompt and boom, perfect image on the first try every time. In fact, for every single prompt, they don't just generate one image.
Right, they generate 512 samples, don't they?
Yes, 512 completely different samples for every prompt, which again takes a massive amount of computing power. Right.
Then they use a completely separate contrastive model, which is essentially a judge that looks at an image and a caption and scores how well they match to rank all 512 of them.
So it's almost like a language-guided search. The generator just throws 512 slightly different ideas at the wall, and the judging model picks the one that sticks best.
Correct. It's a filtering process. And without that re-ranking step, the average quality drops significantly. The raw model might misunderstand the prompt, or put the sweater on the dog, or just produce a weirdly garbled image.
It's basically playing the lottery 512 times to guarantee a winning ticket.
That's a great way to put it.
And there's also the issue of blurriness, right? That was mentioned a few times.
Right, and that directly goes back to that compression we talked about in stage 1, the dVAE.
Oh, right, because it's squashing the image down.
Exactly. The transformer is predicting tokens from a code book, not raw pixels.
All right.
So when the dVAE has to decode and reconstruct the final image from those 1,000 tokens, it inevitably loses the high-frequency detail. So it's not going to look like a razor-sharp 4K photograph. It might look a little bit painted or sort of smoothed over.
Yeah, a bit soft around the edges. And the model also noticeably struggled with certain highly specialized data sets, like birds.
Which seems oddly specific. Why birds?
They specifically tested it on the CUB dataset, which is a famous benchmark all about identifying extremely specific bird species.
Ah, okay.
The DALL-E model is a generalist. It knows generally what a bird looks like, but it might not know the subtle microscopic differences in beak shape between two specific types of warblers that a smaller, specialized model would catch immediately.
It trades hyperspecificity for total generality.
Exactly. It's the jack of all trades, master of none.
Well, it's definitely a master of drawing tapir accordions, which I would argue is significantly more important than a warbler.
Honestly, in the grand scheme of AI research, demonstrating that kind of conceptual flexibility is perhaps far more important than identifying a specific bird.
Definitely. So let's wrap this deep dive up. What is the big overarching takeaway here? Because we went from people trying to painstakingly hand code rules for generating images or training these highly brittle specific models for tiny tasks to this massive brute force but oddly elegant approach.
The real takeaway is that the entire field moved from finding better modeling assumptions, trying to be clever with the neural network architecture, to simply scaling up.
Just throw more data and compute at it.
Exactly. They took a very flexible architecture, the transformer, which fundamentally just treats everything as a sequence. They fed it a single stream of combined text and image tokens. They gave it an absurd amount of data, 250 million pairs, and they solved the incredibly hard engineering bottlenecks to just let it run.
And out of that incredibly simple, brutally large recipe came these deeply complex behaviors. Variable binding, object segmentation, zero-shot style transfer.
It really confirms the hypothesis that if you just have enough data and enough compute, a simple, flexible algorithm can learn to model the structure of the real world in surprisingly deep ways. It didn't just learn to blindly copy pixels. It learned the underlying physical rules of how visual concepts combine.
It's the unreasonable effectiveness of data all over again.
It really, really is.
Well, here is my final thought for you listening. If this model back, when this paper was first written, could spontaneously learn to sketch a cat or properly dress a hedgehog just by reading text tokens, what other capabilities are hiding in these massive models right now that we haven't even thought to test for?
That is exactly the question that keeps AI researchers up at night. The latent space in these models is just vast, and we have only explored a tiny, tiny corner of it.
What can they do that we just haven't asked them to do yet? It's wild to think about. And on that note, do yourself a huge favor today. Go to your search engine of choice and look up tapir accordion AI. You absolutely won't regret it. Thanks for taking this deep dive with us.
See you next time.